Tell me, what questions do you have? Would you like to work some types of problems, or do you like to work exercises similar with the ones seen at the last seminar with the Laplace transform?
Yes, Laplace would be great if we could practice some more.
Okay. Just a sec. Oh, what? And let me search some exercises. Oh, let's see. I would like to make more problems in which you know the image function and you want to find the original function, because you will need this type of problems a lot this week when we'll solve equations and systems of equations using Laplace. So I will insist today on finding the original. The title is the Laplace transform. And first you have to determine the function of s equals 3x plus 8 over s squared plus 4 times s minus 5. B. F of s is 1 over p squared minus 4p minus 12. C. Oh, sorry, f of s squared minus 4s. F of s, let's see, is 1 over s squared plus s plus 5 times s minus 1. And I think that it's enough for the beginning. Then we'll see other examples. Okay. Let's take a look at the first example. I've told you that in general, you have two methods for finding the original functions. So for finding the original, and f of s of sum of simple fractions and use some formulas. Now try to get the formulas. And then we can use formula, which tells you that f of t, which is the original, is the sum of the residues computed in all the singular points from the function e at. You have here the exponential function, which must be written. So this is s. Okay, s is the new variable t is times f of s. And you must consider all the singular points, no matter if they are in the upper half plane or the other half plane. And I've told you that f of t is called the original. And f of s is called the image. Oh, so I'm going to write now the formulas. So you know that Laplace of t at m seen in variable is a fraction over s at n plus 1. And you have some particular cases here when n is 0, you have Laplace of 1, which is 1 over s. And when n is 1, you have Laplace of t, which is 1 factorial over s squared. Then, Laplace of e at 80, computed in the variable s, 1 over s minus 8. Laplace of cosine of 80 in s is s over s squared plus a squared. Then Laplace of sine of 80 in variable s is a over s squared plus a squared. Laplace of hyperbolic cosine, I'm going to write cos h, but you can write also ch. Cos h of 80 in variable s is s over s squared minus a squared. And Laplace of hyperbolic sine of 80 computed in s is a over s squared minus a squared. Okay, so these are the formulas, these are the methods that you can use. I must make some screens. It's for the project, so must take a print screen. And let's see how we can solve the first point. Okay, so for a, f of s is 3s plus 8 over s plus 4 times s minus 1. Use both methods. Let's use method 1. Let's say that this is M1, method 1, method 2. So, method 1. Let's write f of s as a sum of simple fractions. How many simple fractions do you need here? How many?
3.
Let's see. Why did you say 3?
Actually, no, 2, I'm sorry. We would have had 3 if one of the parentheses was z second power.
Yes, exactly. So in this case, we have a product of two expressions. For this one, delta is negative. And for this one, you have a polynomial of degree 1. So the sum looks in this way, s squared plus 4, and here s minus 5. What we should have here, a denominator. Of degree?
Polynomial of first degree.
Yes, indeed. So we must have a times x plus b, and here a constant. Okay, and we find c. Now we are to multiply this expression by the denominator of the first fraction of this one. And we get that 3s plus 8 equals. I have a times s plus b times s minus 5 plus c times s squared plus 4. How do we find a, b, and c now? Well, we should do what?
The parentheses equalize the sides to
Yeah,
see the coefficients of each power of s.
indeed. Indeed. In this case, we should make some computations here. So you have a times s squared from here minus 5 times a times s plus times s minus 4b plus s squared times c plus 4c. Okay, we have that 3s plus 8 equals, we have c s squared times a and c, a plus c, okay, plus s times, we have here minus 5a, minus 5a, plus bs, so plus b, and the three terms are 4c and minus 5b. So the coefficient of s squared in the left side is 0, and the coefficient of s squared in the right side is a plus c, so a plus c is 0. Yes, the coefficient of s in the left side is 3 here, minus 5a plus b, so this one is 3. And 4c minus 5b from here is 8. So in this case, we can write that c is minus 8. And here we have that is 3 plus 5a. Okay, we press b and c using a. So using now the last equation, we get that 4 minus 5 times this one is 8. Okay, so you have minus 25 minus 4 minus 29a minus 15 is 8. So you have here 23, so a is minus 23 over 29. Okay, let's check again if the computations are correct. So we see that we have this sum here. Okay, they seem correct. a plus c minus 5a plus b and 4c minus 5b. Okay, so this is a, and it means that c will be 23 over 29, and b is 3 plus 5 this one, so it's 3 minus 5 times 23 over 29. Okay, and here we must make some calculation, but I think that we'll work A, B, and C in this way, and then in the end, in the final expression of the function, you will replace them by fractions, because it's easier in this way. So let's write f of s. We know that this fraction is f of s, and this is as plus b, and because they have so ugly expressions, I'm going to write in this way: a times s over s squared plus 4, so, plus b times 1 over s squared plus 4. Okay, and I'm going to write this fraction of c times 1 over s minus. So this is a times, this is a plus of what function? So let's take a look at this list of formulas. Okay, let's go. You have here s over s squared plus 4. Okay, s over s squared plus 4. This is Laplace of what function? Well, let's take a look here. You have what function in your case? A squared is 4. Okay, so this is actually s over s squared plus 2 squared. So it means that you have solved cosine of 2t computed in s. Okay, because if you take a look at this formula and replace a by 2, you get s over s squared plus 4, which is your function from here. Then you have plus b times, this is Laplace of what function? Well, we have seen that Laplace of sine of t opposed to x is a over s squared plus a squared. But you don't have here a. So in this case, a is again 2. You don't have here a, which is 2. So it must, this function must be completed in the following way. You have 1 over s squared plus 4, which is 1 over 2 times 2 over s squared plus 4. And this is 1 over 2 times, and this is Laplace of sine of 2t in variable s. But you know that the Laplace transform is a linear application. So this is actually equal to Laplace of 1 over 2 times sine of 2t. of variable s. Okay, so this is 2 times sine of 2t plus 3 times Laplace of what function? Do you hear me?
Is it the function e at the power of 5t?
It's e 5t because a is 5 in this case. Okay, so this is e at 5t. So let's take a look here. In the end, we will have that f of s is Laplace of, let's use again the linearity of this operator Laplace, and we'll get a times cosine of 2t plus b times 1 over 2 times sine of 2t plus c times 5 compute. So these constants come here and Laplace. So it means that f of t will be exactly this expression. But to replace a, b, and c by the values that we have found here earlier. Okay. Just replace a, b, and c. Okay, let me take another print screen. Do you have questions until now? So if you don't have questions, let's do the second method. So this will have number. Let's try to create using method number. Going to
Could you please show the previous slide just for a second?
Yes, sure.
Thank you. Okay, thank you.
For f of s, you're welcome, is 3s plus 8 over s squared plus 4 times s minus 1. Well, if we want to apply this method, you must write first this function e at st times f of s, and then you have to find the singular points of this function and so on. The variable of this function is the variable of f, so it's s. T is just a constant in this case. So let me write the function e at st times s, which is e at st times. Okay. For simplicity, we'll denote this one by g of s, capital G of s. The singular points of g are found by solving the equation denominator equals 0. Okay, so we have from this one s1, which is minus 2i, and s2, which is 2i. And from s minus 5 equals 0, we have s3. What type of singular points do we have here? What type of singular points?
Poles?
Yes, they are poles of what?
Order 1.
Exactly. They are poles of order 1. So we have to find first the residue of the function g of f in the point s equals minus 2i. And this is the limit when s, because is the variable, s goes to minus 2i from. We have here s minus the pole, so here we write s plus 2i. The power of pole, which is 1, times the function g of s, which is this one. But what we should do with the denominator of this function? How should we write the denominator? Well, because since s plus 2 doesn't appear here, we have to write it in which way?
We split it. We're gonna have s plus 2i times s minus 2i.
Exactly. With no derivative here, we have a simplification, and in the end, it minus 2i t times 3s means minus 6i plus 8 over minus 4 times minus 2 minus 5. Let's write plus. Okay, then the residue of this function in s equals 2. This will be the limit when s goes to 2i from this one. Okay, and in this case, we must add them and make some simplifications, but first let's find the last residue. Let me write, I'm not going to write here. This time I won't write s squared for as a product because I already have simplification, and I get 23 here 5t over 29. And if you take a look here and here, you will see that you have the same function because c, in this case, was actually 23 over 29, okay? So in the end, the first method, you had 23 over 29 times e at 5t. This was the last function. And our last function, this one is correct. But now we must add these functions in order to find the first part of the original function. Okay, so let's add these functions. If you have 4i here and here, so this is a common factor, I will write separately this one plus this one, and then we'll add them to obtain the original function. So is g plus residual g equal to. So 1 over 4 is the common factor here. And you have e at minus 2it, which must be written using the Euler's formula. Do you remember the Euler's formula? E at it or I alpha is
Cosine alpha plus I sine alpha.
exactly. So in this case, you have to apply this formula here and also. And let's see. You have 8 6 times cosine with alpha in the first case. Alpha is here. Alpha is, well, what is multiplied by I?
40.
2t.
Just minus 2t without I. Cosine minus 2t plus I sine of minus 2t. Okay, this one over 2i plus 5. Plus, and here we have the sum and the difference of the denominator. 8 plus 6i times. Have cosine of 2t this time because you don't have a minus here at the exponent. Okay? So here alpha is 2t. And you have 2i minus 5. Okay. Then we must amplify with 2i minus 5 and 2i plus 5. And we get, let's see the computations here quickly. We get 16i from here and 30i from here. Okay, so in the end we have 46i. And we have minus 40 plus, because we have an I minus 12. So it's minus 30 plus 12 is minus 28. Okay, this is the multiplication. Times, we have here cosine of 2t, because cosine is an odd function, minus I sine of 2t, because sine is an even function, plus, I'm going to make the multiplications here. Here we have, first with I, we have 5 times 6i, 30, plus 16 is 6i, and we have 40 minus 12. Okay, so this is 28. And then cosine of 2t plus I sine of 2t all over. Let's see, we don't need this bracket. Over this one times this one, okay, which is the result. This one squared, okay, so we have here 2i squared minus 5 squared. And we have 1 over 4i times this one, so this is minus 4, but you have minus 25, so this is minus 29 times this one. must make the multiplication, and we have 46i times cosine of 2t. I squared with this one is a plus, we have plus 46 sine of 2t. And then we get minus 28 cosine of 2t. And plus I times 28 sine of 2t. Okay, so let's just have this one plus this one. Okay, and this one and this one. Okay, is correct. Then plus, let's take a look here. Plus 46i cosine of 2t minus 46 sine of 2t plus 28 cosine of 2t plus 28 times I times sine of 2t. So you have minus plus, and you get 1 over 4i times minus 29 times. This one twice is gonna be 92i cosine of 2t, and this one twice is 56i sine of 2t. This I disappears from here. So we have, actually we have a simplification here, 92 over 4 times 29 cosine of 2t. So with a minus, plus, minus 56, this minus, over 4 times 29 sine of 2t. Okay, actually you have a simplification here, and this is 23 minus 23 over 29. And this one is 14. Okay, so in the end, your function will be this one plus this one plus this one. Okay, so f of t will be this one, which is minus 23 over 29 cosine of 2t. And you can notice here that this is the value of a from the first method. We haven't computed p, but this is p minus 29 sine of t. And we must add this of the first two residues. We must add this one, 23 over 29 here at 5t. Okay, and this is the original function. You must obtain first the same function. And it is the same function. Okay, do you have questions until now? Tell me something that you didn't understand.
It's just so many computations.
Yes,
Very
yes,
long.
actually, indeed, this wasn't such a nice example. The computations indeed were very long, but you will have computations easier than this. It depends on the function. Using the first method here was, from my point of view, easier than using the second one, because here you have found quickly A, B, and C, and then you used some formulas to see that these are the Laplace transforms of these functions, and the computations were not so long. But when you try to solve this using the second method, the problem is that complex solutions. And when you have complex solutions, like in this case, in the end, you'll have an exponential with complex exponent. And when you have this case, you must apply this formula, and also you must make this type of computations then. So when you have this type of function with a polynomial of degree 2 with delta less than 0 and a polynomial of degree 1, the best method is the first one. Yes?
Yes.
Because you have few computations here, but let's suppose squared. If this was squared, then you would have here 3 fractions. And the computations, well, were as long as the ones from method 2, actually.
So when we have squares, we use the second one. If we don't have squares, we prefer the first one. No?
There is another method here which combines the first with the second method. So if you square here, you can use the first method, and for these two fractions, you can use the formulas to see that the original functions look in this way. And for the last fraction, the one with square here, you can use the Meillet-Fourier formula. So you can take this one separately to apply the Meillet-Fourier formula just for this one with a square here, and then to add the result with the results obtained here.
Thank you.
Welcome. But no matter the method you use, you will see that when you have square here, it takes you to okay. Other questions here? Okay, so if you don't have other questions, please try to solve point B. I will give you 10 minutes to solve point B, and you choose the method that you want to use. Okay, choose a method and Have you succeeded to find a solution, or do you need more time?
I think I did it.
Okay, which method did you use?
The first one.
Okay, the first one. How did you apply the first method?
So s power 2 minus 4s minus 12 is actually s minus 6 multiplied by s plus 2.
Yes,
And then we have that s multiplied by a plus b will be
okay.
0, and 2a minus 6b will be 1.
So this one was 0 over it was 4, right?
I'm sorry, I didn't hear.
Okay, so this was the equation, right? And you found solutions. Please tell me again.
Oh, we have 6 and minus 2.
6 and minus 2. The product is minus 12 and the sum is 4. Okay, it's perfect. So f of s over square was right over s minus 6 plus b over s plus 2. Okay, you multiply this one by s minus 6 times s plus 2 because actually this is the denominator. And you had that one is a times s plus 2 plus b times s minus 6. Okay, this is not 5. And you get that is s times a plus b plus 2a minus 6b. Okay, your system was
A is 1 over 8 and b is minus 1 over 8.
yes, because here a plus b must be 0. Okay, so they check this condition. And 2a minus 6b must be 1. So 2 times this one plus 2 times this one is 1. Okay, it's perfect. This is the solution, indeed.
And then we're gonna have 1 over 8, the Laplacian transform of e power 6t.
Yes, this one times this one. Okay, way.
Minus 1 over 8 times 1 over s plus 2.
Yes, and this is the Laplace of,
E power 6t.
yes. And this is Laplace of,
E power 2t.
yes, but with a minus.
Sorry,
Okay,
minus 2. Yes.
and you know that Laplace is so 8 e at 60 minus 1 over 8 e at minus 2t, all computed in s. So our function f of t will be this one. Okay, and if you use the second method, see that you'll get the same function. Did some of you try to use the second method? Okay, no one? You don't like residues, right?
Yep.
Okay. Let's move to point C. Let me first take another screenshot. Okay, so this was it. C. Okay, let's take a look. I'm going to let you 5 minutes to solve C using what method you like, and then we're going to discuss. Okay, if you need time, I'll give you more time, but try to write something in 5 minutes.
Teacher, it says s
Yes.
power 2 plus s plus 5 or plus 5. I can't see.
Plus 5. This is 5.
Okay, thank you.
Welcome. This is 5 and this is S. Did you manage to find the first bit?
I have ugly numbers.
Yes, indeed. So in the first method, so which choice?
I used the second method.
Yes, because if you compute the delta for this one, you will see that this is
Negative.
yes, indeed.
Complex.
So, indeed, the it's minus 9. So is that, and if you want to use the first method, you will see that you will be able to use it because you have to write this function f of s as a sum of two simple fractions. I mean, you won't be able to use just the first method. You can combine these two methods if you like. You have here something of degree 1, as plus b, and here a constant c. So if you want to use the first method, you have to find a, b, and c. And after that, for this one, you can apply a formula. You can use a formula to find the original. And for this one, how do we find the original? Using,
The residue.
yes, using the Mellin-Fourier formula or the one with residue. So, this method would lead you to less computations here for Mellin-Fourier formula. If you want to compute just residues, you can use method 2. Okay, to write as and find some residues of this for you. If you try to solve using the second method, you will see that you have similar computations with this one. And I know that you don't have such nice values, so let's try to mix them. So let's use the first method combined with the second one, actually. So let's use this idea. If we want to find A, B, and C, we have to write the initial equation. And with the denominator. So what's A times S plus B times S minus 1 C times S squared plus S plus 5. So 1 is S squared times A minus S times A from here, okay, plus B times S minus B plus C times S squared plus C times S plus 5C. And we have the system. A plus C is 0 because we have the coefficient 0 in the left side. Then minus A plus B plus C is 0. And 5C minus B is 1. Okay, so C is minus A. From here, C is minus A. So we have B is 2A. And them together, we get that 5C, so minus 5A, minus B, so minus 2A is 1. Okay, so A is minus 1 over 7. B will be 2A, so it's minus 2 over 7. And C is minus A, so it's 1 over 7. Okay, and these are the coefficients. For the last fraction, we know the original function. And we have to replace here A and B to see the original function for this one too. Okay, so f of s is minus 1 over 7 times s minus 2 over 7. Okay, these were A and B. S squared plus s plus 5. And I have a minus 1 over 7 here times s plus 2 here over this one. Okay, let's take this function. And let's multiply by e at st. And for this one, we must apply the Mellin-Fourier formula. When you find the singular points of g of s, you solve this equation. And you have s1 is minus 1 plus square root of 90 times 2. And s2 is minus 1 square root of 90. Okay, so it means that the residue of g of s in S1 will be limit, let's use S1 and S2. Limit s goes to S1 from s minus S1 times this one, s minus S1, s minus S2, because we are going to write this denominator in this way. We have a simplification, and we have S2 plus 2 times S2 over S1 minus S2. Okay, and the residue in S2 will be the limit when S goes to S2. We have S minus S1 here and S plus 2 times E at ST. I'm writing what I did after simplification. So in the end, you have S, sorry, here was S1. S1, not S2, S1 and S1. And S2 plus 2 times E at S2t. I was thinking about the expression over S2 minus S1. And the advantage here is that when you add this residue, you get that sum is actually a fraction, because I'm going to write it in this way. And the sum is S1 plus 2 is S1t minus S2 plus 2 is S2t over S1 minus S2. So you don't have to make amplifications yet. But of course, you have to replace S1 and S2 to get this function. Then you have to multiply this function by minus 1 over 7. And this will be the residue for this function. Okay, let's say you're not f but f1, okay? Because f is the entire sum, and let's say that f1 is this one. F1. You won't have something like this at the final expression. I want to discuss this because if you have something which has the same pattern but less computations, you will know what to do here, okay? Just for this reason, but you will have uh, numbers which are not so ugly here. We are discussing now the okay, because we have simple calculations. Do you have questions now? Okay, so if you don't have questions, let's see other examples. The same case for f as which is 1 over p squared times p squared plus 3, and b f of s is 1 over p squared times p squared plus 4 squared. Okay, I'm going to give you 5 minutes to try to solve A, and then we discuss. Did you manage? Sorry, instead of P, you have S. Sorry. I have written these examples from a book, and the notations are with P, and also I have used the notation with P for many years. I'm not used with S, so I have changed the notation in that S in the course, and I've told you that, so I wanted to have the same notation, and now when I wrote, I forgot that you have S. Okay, so this is S, of course, not P. Have you succeeded to to find the original?
No.
Okay, let's take a look at A. What method have you tried?
I tried the one with t power n, but then n has to be positive. It cannot be -2.
But just a second. If you want to be as sum of
Oh, I thought it was with the other one. The other type of problem, sorry.
okay, it's fine. Let's try to solve using the first method. You have this function which has to be written as a sum of how many functions? How many?
Is it 3? Or
Yes, 3. One with s squared. S squared plus 3 here. Okay, and here you have a constant, here you have another constant, and here you have c times s plus d. And you find a, b, c, and so you multiply with s squared times s squared plus 3. And you have 1 equals, let's see this one. This one is a times s squared plus 3. This one is b times s squared plus 3. This one is c times s plus d times s squared. So 1 equals a times s cubed plus 3s plus b times s squared plus 3. Okay, plus c times s squared plus ds squared. A plus b, okay, here, plus s squared times b plus d from here and here. And you have 3 times a times s from here and plus 3b from here. Okay, so you get that a plus c is 0, that b plus d is 0, then 3a is 0 because you don't have s here, and 3b is 1. Okay, so you get that c is minus a is 0, so c will be 0. Then here b is 1 over 3, and d is minus b, so is minus 1 over 3. Okay. At the end, you get that s is equal to a is 0. Okay, so we don't have this fraction. B is 1 over 3, so we have 1 over 3 times 1 over s squared, plus c is 0 again, and d is minus 1 over 3, so I have minus 1 over 3 times 1 over s squared plus 3. Or, from the beginning, you could have written f of s in this way. This is 1 over 3 times 3 over s squared plus 3 times s squared. Because if you take here, you will see that the difference between this one and this one is 3. So if you write here 3 and put on 1 over 3 in front of this fraction, you will be able to write again this 3 as a difference between s squared plus 3 and s squared. So this is s squared plus 3 minus s squared over s squared plus 3 times s squared. And in the end, we get 1 over 3 times. And this one for this fraction is 1 over s squared minus 1 over 3 times, when you have the simplification, this is 1 over s squared plus 3. So it's the same thing. Okay, and this is faster than this one. So this way, this method helps you to find directly the fractions. And now let me write again the function f. So f of s is 1 over 3 times 1 over s squared minus 1 over 3 times this one. This is the plus of which one?
Is it of 2?
Of t. Because Laplace of n applied to s is n factorial over s at n plus 1, right?
Yes.
So n plus 1 is 1. Sorry, n plus 1 is 2 from here. So n is 1. So we have that Laplace of t is 1 over s squared. Okay, so this is the Laplace of t. And this one written in this way, 1 over 9 times 3 over s, well, 9, not 3, sorry, square root of 3. And here I have 3 square root of 3. Because this one is s squared plus square root of 3 squared, and I need to put here a to have the sign, okay? So this is 1 over 3 times Laplace of t minus this constant times Laplace of sine square root of 3 t. And in the end, I have the limit of this operator. This is 1 over 3 times t minus 1 times sine square root of 3. And the function f of t, the original function, is this one. Okay, do you have questions?
Teacher, I do. How do we know which fraction, which denominators to choose at the beginning? According to what?
Where? Can you be more specific, please? Where? Oh,
Yes, when
here?
you wrote the a over s. Yes, yes, this.
So you have s, which is something of 1. And denominator must be a constant. Then, if you put the power of this s, it doesn't matter that is the power 2 or 3 or 4 or something else. If here you have a constant, then you will put here again a constant. Okay?
Yes.
Because you have this one at power 2, but it doesn't matter because delta here is negative. So you have to put again constant. But here in this case, delta is negative. And because you have here something degree 2 with delta negative, you must put here something of degree 1, which is in this. have I succeeded to answer the question?
Yes, thank you.
Okay, welcome. What other questions do you have? Okay, so this one was very, very simple. Let's take a look at B. I will give you 5 minutes again to think about how we can solve this point B. Okay, think about it 5 minutes and then we talk. What method could you use here? Uh,
The second one.
The, and the second method implies computing the residue of three singular points, which are 0, 2i, and minus 2i, and all of them are poles of order
2.
2 indeed. So you have many computations to do here. Let's try to mix the first and the second method. So x1 x squared x squared squared. So if we want to use the first method, we must write this as a simple fraction. How many fractions do you need here? How many fractions?
Is it 4?
Yes. What should I write here?
A,
Here?
B,
Here?
CS plus D, I think.
Yes. And here?
Uh, is it gonna be E since we have a degree of 2? Oh,
No, it has degree 1 because here you had degree 1, so you have the same type of polynomial as here. Okay? Yes, plus, okay, let's say H.
F. Oh, yes.
No matter you have this expression to the power 2 or 3, it doesn't matter. You must have the same type of polynomial as here. Okay, this one will be written here, but using another constant. Because in this case, this one was here, but was a constant also. Okay, and you have to find A, B, C, D, E, and H. For this one, you have a formula. For this one, you have a formula. For this one, you have a formula. And just for this one, you can apply the Mellin Fourier transform. Let's say that this one is the function f1 of s. For this one, you apply the Mellin Fourier formula. You must multiply this function by st, and then you find singular points, which are 2i and minus 2i, which are poles of order 2, and you make the computation of the residue and you add them, but of course you have a lot of computations to do. I just wanted to discuss the methods that you can use here. Okay, let's skip the computations. Let's see another function f of s. Let's take a look at this one. 1 over s cubed times s squared. I'll let you 2 minutes to think about this function, to think about what method could we use here, and then we discuss. So what do you think? What could we apply here?
We could also mix
Second.
again, but this time we have 5.
Yes, indeed. We could also mix them, but we could also use the second method. Let's see, if we use the first method, then we would have that f of s, which is this one, is a sum indeed of 5 fractions. Here,
A, B,
here,
C,
yes.
and then DS plus E. Ah,
I have
I don't
view
have power 2.
one again. So I have here a constant. And then,
Again, a constant.
yes, get the constant. Let's make some computations. We multiply this one by s cubed times s minus 1 squared, and we get that 1 is a times s squared times s minus 1 squared, then plus b times, have a simplification here, s times s minus 1 squared, plus c times s minus 1 squared, plus d times s cubed s minus 1, plus e times s cubed. This is s to the fourth minus 2s cubed plus s squared. Then we have s cubed minus 2s squared plus s plus c times s squared minus 2s plus 1 plus d times s to the fourth minus s cubed plus e times s cubed. Okay, and here I'm going to write the equations. For s to the fourth, I have a here and d here. So a plus d is 0 because I'm looking at this expression. Then for s cubed, I have minus 2a from here plus from here minus b from here and plus e from here. And also then for s squared, I have a from here minus 2b from here plus c from here, and that's all, and it's 0. For s, I have not a term here. Here I have b minus c from here, and that's all, and this is 0. And the term appears here, and c is 1. Okay. So let's see the solution of this system. C is 1, b minus 2c is 0, so b is 2. Okay, c is 1, b is 2, b is 2, c is 1, so that is 3 from here. It's 3. It's 3, so minus 6. B is 2 plus 2, so it's minus 4. So I have that minus 4 minus d plus e is 0 from here. And I have that d is minus 8. So it's minus 3. So using this, I get that minus 4 plus 3, so minus 1 plus e is 0, so e is 1. And let's see the function f of s. What's s? S squared, s cubed, s minus 1, s minus 1 squared. Here we see which is 3, b is 2, c is 1, d is minus 3, and e is 1. So actually, f of s is equal to 3 times Laplace of 1 over s. Is Laplace of which function?
Is it 1?
Yes. 1. Plus times Laplace of
T.
yes. Let's see how to solve square cube. So this is 2 factorial over s cubed. Okay, so this is 2 over s cubed. So in this case, we must write this function as 1 over 2 times 2 over s cubed. Okay, so this is 1 over 2 times Laplace of t squared of s, because Laplace of t squared is 2 over s cubed, and when you have the simplification, you get this function. Laplace of
E power T.
yeah, and the last one must be found. We don't know this one. So we take the function g of s to be equal to 1 over s minus 1 squared times e at st. The singular points are actually p equals 1, which is what?
A pole of order 2.
Exactly. So we are looking at this function now. This is a pole of order 2, and the zero of the function g of s in s equals 1 is the limit when s goes to 1 from s minus 1 squared times the function, and we take the first order derivative, and this is, the derivative is e at st times t, because s is the variable, t is the constant. Okay, so this is e at t times t. Okay, so we have that, let me write in this way, 1 over s minus 1 squared, which is this fraction, is actually Laplace of t e at t, evaluated in s. So in the end, the function f of t is, let's take a look here. We have 3 plus 2t plus 1 over 2 times t squared from here, minus 3 e at t from here, plus this one, plus t e at t from here. This was the combination between the first and the second method. Let's use just the second method to see the difference. So you have the function f of s, which is 1 of s squared, s cubed, sorry, times s minus 1 squared. Let's take a look at here f, which is e at st times 1. The singular points are s equals
0.
yes, which is
Pole of order 3.
yes,
And S equal to 1 pole of order 2.
Yes. Let's find the residue of the function g of s in s equals 0. So this is 1 over 2 because you have 1 over n minus 1 factorial and n is 3. So this is 1 over 2 factorial, which is 1 over 2, okay? Times the limit when s goes to 0 from s minus 0, which is s at the power of the order, times this function. And we must take the derivative of order 2, because the order is 3. We have a simplification, and we do when it goes to 0 from, let's see the first derivative. Is the derivative of this one, which is t e at st, times s minus 1 squared minus this one times the derivative of this function over this one squared. And again, we must take the derivative. Have 1 over 2 when s goes to 0 from. Let's make a simplification here. So we have e at st times st minus t from here, minus 2 from here, okay, over s. And this is 1 over 2 times limit when s goes to 0 from. The derivative of this one must be computed as a product. So when you compute the derivative of this one, you have the derivative of the exponential, which is t e at st, times st minus t minus 2, plus the exponential function times the derivative of this one, but this is the variable, it's a constant. So the derivative of this one will be just t, because this is a constant. This is a constant. And now the derivative of this expression, we have to multiply it by s minus 1 cubed. Then we have to subtract this initial function times the derivative of this one, which is this one, over s minus 1 to the power 6. And then we have to replace s by 0, and that's t times t minus 2. Okay, so s is 0. This is 1. This is 0. Plus t times minus 1 minus t minus 2 times 3 times 1 over 1. Okay, this is minus 1, this is 1, this is 0, this is 1. So we get 1 over 2 times. We have minus t squared minus t times minus 1, this is t squared plus t. This one. This one is t squared plus t. And you have a plus from here, 3t plus 6. Okay. This is times t squared plus 4 plus 6. This is the residue in s equals 0. And we have to find the residue in s equals 1. Okay, so the residue of g of s equals 1 is limit to s goes to from s minus 1 squared times this one and you take the derivative. You have a simplification, and this is t e at st times s cubed minus the function times 3s squared over s to the sixth. S is 1, so t e at t minus e at t times 3, and this is it. Okay, so the function f of t will be the residue in 1 plus the residue in 0. And that's all. Do you have questions? Okay, so if you don't have questions, give me a minute to download the attendance list. Just a second. George, do you hear me?
Present.
Okay. Anna, are you here? Or maybe. Let's see. Andra, can you hear me?
Yes.
Okay. Vlad?
Yes, I'm here. I can hear you.
Okay, that's perfect. Your colleague Islam left. Petre, Georgia?
Here, I'm here.
Okay. Leila, I've talked to you a lot, so I know that you are here. Hi,
Sunt
guys.
prezent Mihai
Okay.
Antoniu Ceaușescu.
I'm here. I'm here.
Okay, that's perfect. Mario?
I'm here.
Okay. And Oblu?
Here.
Alexandra. Okay, that's perfect. Do you have questions? Okay, if not, thank you. Have a nice day. See you on Thursday. Goodbye.
Thank you.
Goodbye.
Goodbye.
Thank you.
Goodbye.
Goodbye.